Hello and welcome to the next series of short videos, this time about the fascinating topic of op-amps. Incredibly useful little integrated circuits whose function is to amplify up the difference between two input voltages. We'll start this one with a review of what op-amps look like, how to wire them up, and the characteristics of an ideal op-amp. One of the most useful things about designing with op-amps is that while real op-amps are not ideal, they are in many cases close enough to ideal op-amps in behaviour that you can design circuits assuming that your op-amps do behave like ideal components. This makes designing op-amp circuits much easier than designing with discrete transistors. So let's have a look at what an op-amp looks like. That's an op-amp. As you see, tiny little thing, although this is a comparatively large package for an op-amp these days. I'll just zoom in a bit. Okay, and you can see that this thing has 8 legs, 4 on one side and 4 on the other. And you might just be able to see that there is a little indent at this end of the package here, and a small circle on the top of the body of the op-amp just at that point there. The small circle indicates, there you can see the circle there. The small circle indicates pin 1. It's part of a standard with electronic packages that a circle indicates pin 1 and then the pins are numbered anti-clockwise. Another example of the rule, everything goes anti-clockwise except clocks. There is a standard for the pinout of a single op-amp in an 8-pin package like this, and that's this one. Op-amps are amplifiers, which means that in many cases the output voltage is greater than the input voltage. And the only way to get an output voltage greater than the input voltage is if the amplifier has some type of power supply that it can draw on. And the power supply for an op-amp is on pins 7 and pin 4 in a single op-amp package. Pin 7, the positive power supply, pin 4, the negative power supply. Pin 6 is the output voltage, and pins 3 and pins 2 are the two input voltages. Remember, the function of an op-amp is to amplify the difference between the voltages on its two inputs. For a single op-amp, pins 1 and pins 5 are often used to null out the offset voltage. More about that later. A revision of what these pins actually do then, and an introduction of the circuit symbol of an op-amp. We'll draw op-amps like this, a triangle. And the two inputs are on this side of the triangle. One of them has a plus next to it, and the other one has a negative next to it. This is known as the non-inverting input. This is known as the inverting input. The output comes out of the apex of the triangle there. So this is V out. This I'll call V plus. The non-inverting input voltage. This I will call V minus. The inverting input voltage. And the function of an op-amp is to put its output equal to a large number A, called the open loop gain, times the difference between the two input voltages, V plus minus V minus. Sometimes we don't bother to draw the power supply pins, but it's important to remember that they are always there. An op-amp will not do anything unless you turn it on, you give it a power supply. In this particular case, our power supply, the positive is set to VCC and the negative minus VCC, or VCC minus. Now, let's look at the properties of this amplifier. Properties of an ideal op-amp. Standard exam question. 1. An ideal op-amp, we assume that the gain, the open loop gain A here, is infinite. 2. Perfect differential gain. We assume that the output is proportional to the difference between the two input voltages. 3. We assume that there is no current flowing in to either of these inputs. That's a particularly important property and makes designing circuits with op-amps particularly simple. 4. We will assume that there is no output resistance. In other words, if we were to model the output of this op-amp here as a Thevenin equivalent, it would have a voltage source of Vout and a Thevenin equivalent resistance there. That resistance there would be 0. So you can take any amount of current out of the output that you like. The voltage at the output is not going to change. 5 and 6. The inputs and the outputs can go anywhere between the positive power supply and the negative power supply. Now, real op-amps don't behave like ideal op-amps. The input currents are not 0. However, they can be negligibly small, down to picoamps or even less than that in high-performance op-amps. The offset voltage is not 0. Now, the offset voltage is a small error in the calculation of the output voltage for real op-amps. For real op-amps, the output is not the open loop gain times the difference between the voltages on its inputs. There is this error term known as the input offset voltage in the expression as well. That can be of the order of millivolts in typical op-amps. And this can be an issue if you're looking for high accuracy measurements down at DC. But there are circuit techniques to get around that, and we'll talk about those in later videos as well. The outputs cannot quite reach the positive and negative supply rail. But again, in some designs they can get very, very close. So the difference is negligible. Op-amps in which the output can effectively get to the positive and negative power rails are known as op-amps with rail-to-rail outputs. The gain A is not infinite, but it can be extremely large, of the order of 100,000 or 200,000. Perhaps most seriously is that the gain decreases with frequency. Op-amps have a property known as the unity gain bandwidth. It's the frequency at which the gain of the op-amp decreases to 1. And that frequency can be of the order of a megahertz or so. Since it's trying to get down from a low frequency gain of 200,000 down to a gain of 1 at a megahertz, the gain starts to decrease at comparatively low frequencies of the order of tens of hertz. And this is something to be aware of if you're trying to design amplifiers with a large amount of voltage gain at low frequencies. Now, before we leave this first video, just one thing that you may have realized. If an ideal op-amp has an infinite gain, then doesn't that mean that its output is always either positive 12 volts in this case, or negative 12 volts, at the extreme ends of the range that the output can go to? Well, we could ask the simulator. This is an ideal op-amp, in this case powered from plus 12 and minus 12 volts, and the input voltage at the moment is 0 volts, so it's amplifying up the difference between 0 volts here and 0 volts here. Anything times 0 is 0, so we get an output of 0. But for any positive voltage in, the output goes to its maximum of 12 volts. We say that the op-amp is in saturation. This op-amp is trying to multiply about 3 volts minus naught by something which is effectively infinite. It gets an effectively infinite positive result, but it can't put its output to an infinite voltage. It does the best it can, and the best it can is to get to the positive power rail, in this case 12 volts. And a similar thing happens if you give it any negative input. It's doing the best it can to satisfy this formula, but it can't put its output below the negative power rail. We say this op-amp is in negative saturation, and its output is at minus 12 volts. You might be thinking that if I've built a circuit here, which no matter what the input voltage is, provided it's positive, gives plus 12 volts, that's not a very useful amplifier. Its output never changes. Well, in fact, op-amps are incredibly useful amplifiers, provided you know the trick. And the trick is something called negative feedback. And that's the subject of the next of these short talks.